Thanks for having me. Can you hear me okay? Yeah? Okay. I don't want to hold the mic. Thanks for having me. I'm very excited to be here. I know the difficulty of starting up a group for a meetup, so it's really great that everyone's here and we get to talk about nerdy things, which is the most fun part of what I get to do. I only haphazardly have given talks that long. I was sort of forced to for an interview once, and then I didn't have to for a long time. But then after I learned, I'm going to turn my mic off. What that echo is. There we go. Um, after when I lived in the Bay Area and started to learn Scala, I was sort of excited to learn. I was excited to share what I had learned, and a meetup is a great opportunity to do that. So even if you're a beginner or you just learned something cool that you didn't know about before, um, people who run meetups are always desperate for speakers. So please volunteer. And it's great practice, and you have a very welcoming audience, right? Everyone's going to be very welcoming, and we get to learn about these things that people get excited about. It's very exciting. And functional programming for me made programming exciting again. I had done Java for 15 years or something like that, and I was really tired of writing XML configuration files and the usual kind of Java stuff. And then I stumbled upon Scala and had the opportunity to learn it. And I was like, oh, this is so interesting. There's so many new things I can fall into and so many new mistakes I can make. But so many less mistakes I can make overall. There's like a theoretical basis to a lot of what's going on here. There's types and there's these mathematical laws that you can hopefully take advantage of. And there's just kind of a deeper thinking. Maybe all the rules of thumb for object-oriented programming never felt very solid to me. They were it's kind of like somebody made it up, and it's a best practice, but kind of it didn't have any underlying something. It wasn't really standing on something. Whereas I kind of was hoping maybe that there was sort of a physics to programming. Sort of there's some mathematical thing underneath that could help guide us. So I started learning more about it. And so this is a talk I've given a couple times. But if you look up blog posts and academic papers and read about functional programming, this word comes up a lot, and it's algebra. Can everyone see this okay? It should be big enough. And so the term algebra always comes up, and so I kind of wanted to learn about it, and I'm here to share what I learned. So why do these people keep talking about algebras? What's the big deal? Why is this important? Why do we care? And how can it be useful in what we do every day, which is make things that talk HTTP and JSON with other things, or that's sort of a normal that we do. So I'm happy to pause at any time. There's definitely going to be time to ask questions at the end. So whatever you're comfortable with, just shout it out, raise your hand, what have you. I think we'll try and this is a new thing to do the online part, so someone will signal me if there's an online question. So all right, let's go. So this expression here is probably familiar to everybody, or at least it's intelligible in some way. So this is sort of your high school algebra. This is what we're going to start with. So a plus 2b plus 12. There's some parts there, and we can do some operations on them, and we were trained to be able to read this expression. We were trained to know that when we see A's and B's and C's and X's and Y's and things, that those were variables, and then we could do things like multiply them and add them. But we didn't know that before that. We were trained, and now it's probably familiar to most people. So here's another expression, and instead of sort of your high school algebra, this is a Boolean algebra. So it's a little bit more restrictive maybe, or we'll find out, but we can do things like and expressions together and or them, and we can do a not operator. And we do all this. We when we became programmers or were introduced to computers, we learned about Boolean algebra because we had to deal with ifs and elses and all that junk that we have to deal with. So this is my poor graphical skills trying to represent Legos. So here's a 2x2 Lego, and there's another 2x2 Lego, and when you put them together, you get a 2x4 Lego or something like that. I'm going to try and describe, well, how this perhaps has something similar to these other things, these other kinds of algebras. We combine things, and there's kind of rules. You can't stick Legos together haphazardly. There's only a certain way that they can interact. There's a lot of choices, but you can't stick the bumps or whatever they're called on a flat side. You got to stick the bumps on a side that accepts them, and that's the rule. So you can think of functions and types in some way, in a similar way. You can, if you have a function that takes an int, you can't pass something that's a string. You have to pass something that's an int. So they fit in only certain configurations. So we're going to talk about some structure maybe that Legos have also. Because Legos are cool. And here's a different example. This is like some little language that I made up that is describing how to draw something. So on the right-hand side is a circle. And I could draw a circle if I had something where I want to make a path, and sort of on the most inner expression on the right-hand side, I'm going to have 4 parts, 0 to 3, and then for each part, I'm going to take a quarter of a circle arc. There's this arc there, and I'm going to apply a rotation operator to it. So I'm going to rotate it 90 degrees 4 times, and then I'm going to connect those together in a path. And so you could imagine that is, if we take 4 arcs that are a quarter of a circle and we rotate them, then we could draw a circle. I'm going to talk about, well, maybe this has some sort of structure to it also that we can take advantage of, that we can do something with. One thing that we all do all the time is we make new types. And how do we build types? We build types out of other types. So an address is a street and a state in my very poor representation of an address. But we build more complex types out of simpler types, just like we build more complex Legos out of simpler Legos. And this actually has a very algebraic structure that we'll explore. And then finally, maybe something like an API. So this is sort of a description of a REST API or an HTTP API from GitHub, where I can ask for a particular commit for a project, and I can push a commit to a project. And maybe there's something about APIs that is also algebraic. We can manipulate them, we can combine them. So we're going to try and figure out what about these, what properties do all these different kinds of things have that makes them where we can treat them the same. So that's kind of the intro, the way we start thinking algebraically here by example at least. I didn't want to just put up the math. So the talk is important. We have four things to get through. We're going to talk about structure. So what is it about these different examples that is the same across them? We're going to talk about an example of these things in terms of algebraic data types, which we can encode in almost every language that we deal that we can program in. We can do it in Scala, and I'm going to show you how to do it in Scala, but we can do it in other languages. Then when we have something that is algebraic, that's nice. We can say, we can say, yes, I found something that's an algebra. It has algebraic structure. Congratulations, your boss will give you a raise. No, that doesn't happen. But we can do things with our algebra. The power is that when you can say something has these properties, you can use them to your advantage. You can make things faster. You can do things in a different way. You can preserve other things. So that the real point is once you have a structure, you can do something with it. And then finally, they're going to talk about something a bit more that's relevant to what we do as sort of enterprise programmers, or in our actual domains. I'm going to try and motivate how do we encode our domain knowledge and the operations that we have on our domains as algebras, and how that might help you in your development. Okay, so structure. Here's this expression again, and it has structure. So what are the parts of this expression that we can find? Well, there's these symbols that we can sort of parse out. There are variables, there are constants. The 2 and the 12, those are constants, and there's variables, which are usually letters. There's things that we can do with those symbols. We can multiply them. Maybe maybe our notation sort of implies a multiplication. So 2b is actually 2 times b. So there's a little bit of ambiguity that drives computers crazy, but humans can do a good job of parsing that. We can add, we can multiply. Then maybe we can learn fancier things about division or subtraction. But in this example, these are the things you can do. And then there's the things that haunted us in middle school, all the laws, the distributive law and the associative law and the commutative law and the identity law. So, if you, any number plus 0 should always give you the same number back. Any number times 1 should give you the same number back. We've internalized all these, through our education, which is a good thing because it lets us do algebra really quickly in our heads or on paper. But for computers, they don't know any of this stuff. We have to teach them what these laws are. So that's kind of what we're going to say. We're going to say that if this is the example of an algebra, then we have an algebra. And an algebra is made up of symbols, and then the operations we can perform on those symbols. But those operations are constrained by some laws. You can't just combine them willy-nilly. There's some reductions or different things you can do with it. So this is going to be our definition of an algebra. And we're going to apply it in different areas and kind of see how that might help us as programmers. All right, so back to our example. In this algebra, the symbols are the constants and the variables. We have our operations, and we have our big fancy words for our laws. Okay. So now we have some structure. We have an algebra, we have operations and laws. Let's talk about algebraic data type. So how do we map this concept into our little sort of schema for an algebra? So we're dealing with types. We can ignore the algebraic data part of it. We can just talk about types. So the things that we manipulate in our algebraic data type thing that we're going to call an algebra are types. We can have types that are, we can name them however they are. There's some built-in types, some primitive types that we get in our language. We have Boolean and int and long, and the evil string that no one should ever use. And we can make up new types. Well, not yet. We have our base types, right? And then we can build up bigger types out of them. We can make new types out of the smaller types. But then, what about these laws? What are the laws of types and how they combine? Like maybe the compiler is doing it, but how do we say what those laws are? Let's take an example. Let's take A times B. So this is what, and if these were types, like if these were numbers, we know what that means. 2 times 4 is 8. But what does it mean to multiply in the world of types? Well, the natural, I don't know. I don't know if it's the natural implementation, but I'm going to give you some reasons why. But the way that we encode this, at least in Scala, is as a tuple. So A times B, the product of A and B, is both an A and a B. So it's a tuple that contains both a value of type A and a value of type B. And so, okay, that's a product. What are the laws of this thing? Well, if I have a tuple with an A and a B, I basically have the same information if they were in the other order, a B and an A. So we can kind of say that A and B is maybe the same as B and A in the other order. We haven't really lost anything. They're equivalent. So we're going to sort of relax equality and turn it into equivalence. So we can say that A and B is equivalent to B and A. And then we have this associative law. So if we have an A with a pair of B and C's, we can say that is equivalent to an A and a B paired with a C. And it's just sort of manipulating the parentheses. But we haven't lost anything. We haven't gained anything. There's no new knowledge there. They're just, there's a little bit more structure there that we can transform one way or the other. Okay, we're going to do more and more of these to sort of see the pattern that's going on. All right, what about this one? What about A times 1 is A? Well, we know that's true in our high school algebra. And so we know if A times B is to make a tuple, then A times 1, well, what's 1? We need a type. So A is some type. What's the type that means 1 here? Well, so if we made a pair, we need a type that basically says if you pair any type with this type, you basically have just that type anyway. So if I have an A, in Scala, we call this unit. Unit is really a type. It's a type with 1 value. So it's not even a bit. Like a Boolean, there's 2 of them, true and false. Unit, there's just it's a value with, there's only 1 value for that type. So it's not even a bit. So there's like no information in a value of type unit. So if you pair something with a unit, there's nothing new there. It's basically equivalent to just having the type itself. So we're kind of proving in a little bit of a hand-wavy way that types and the way you combine types follows the same algebraic operations and laws as numbers. Ooh. What about this one? Okay, so if you multiply anything by 0, you get 0. So what's 0 as a type? So if I have a pair with an A and some other type that we're going to call 0, I get 0 back. It's like it destroys the A. Well, in Scala, that type is called nothing. So nothing is a type, and if Boolean is the type with 2 values, and unit is the type with 1 value, nothing is the type with 0 values. There are no values of type nothing. And so then we can interpret this expression. If there are no values of type nothing, it means I can never make a tuple because I never have something to put into that second position of the tuple. And so therefore, the left-hand side, I can never make one, and the right-hand side, I can never make one, so it's true. Sort of a weird argument. I can't make a value of that type, so therefore, nothing does equal nothing, which is sort of tautologically true. All right, that's fun. Well, we did multiplication. That was creating a tuple or a pair. What about addition? Well, addition in Scala and in other languages, one way to represent them is with the either type. So the either type it's either an A or a B, but not both. It's one or the other. So it has a value of type A in it, or it has a value of type B in it, and those are the only cases. So we get similar laws. So we can swap the order of the types. So A plus B also equals B plus A. Like, we haven't really lost anything. It's just sort of a positional change. And then we get this associative property too. It's either an A or a B or a C or the other version. And we haven't lost anything. We can say that those types are equivalent. And we have the other one too. We can, if you add 0 to any type, you get just that type back. So I'm either an A or a nothing. I can never produce a value of type nothing, so I could never fill in the right side. So I have to be just the left side. Therefore, either A nothing is the same as just A. All right, this is the fun. This is the big one. Look at this. This is the distributive law. So A times B plus C should be the same as A times B plus A times C. So if we translate that into types, so times is the product, is the pair, and plus is the either. So the A and an either BC is the same as either a pair of ABs or a pair of ACs. So you can convince yourself that that's right. There's always an A, right? That's on the left side. And then you just sort of factor it in, and it works. Yes, math works. We have two cases now that it works. Okay, what about this? Here's our profound statement of the day. 1 plus 1 is 2. So I kind of hinted already. If 1 is unit, 2 is what? So unit is 1, and there's one value of type unit. So what type has two possible values? A bit or a Boolean. Your mic didn't work. They got it back there. So yeah. So maybe 1 plus 1 does equal 2, but in types. So I have either a unit on the left or I have a unit on the right, and that encodes true or false. Left is true and right is false, or vice versa, but it's the same information as a Boolean. Now, you probably don't want to use that encoding of a Boolean because we have a primitive type, but who knows? We'll see what happens. Let's look at this type. 1 plus some type A. So this says I have a unit. I'm either unit or an A. Well, I'm either unit or an A. So I have a value of type A, or I'm just this token that doesn't mean anything. So that's equivalent to option, if you're familiar with option. An option is either some value of type A or nothing. I shouldn't say nothing because it's imprecise in this language, but it's equivalent to unit. It's just a token. A plus A equals 2 times A. Okay, that's a normal law. Well, A plus A is I have either an A on the left or A on the right. And a 2 is a Boolean paired with an A. So if on the left-hand side, if it was a left A, then the right-hand side would be like true in the value, and then the right-hand side would be false and the value there. So these are equivalent. Don't worry, I'm going to get done with this part. Oh, good. I anticipated myself. So we have these algebraic data types. So types have this algebraic structure. So we have our types. We have our primitive types that we get for free from our language. And then we can combine them with the product and the sum algebraically. Those have encodings in our language. So in Scala, product is the tuple, and sum is, we can use the either to do that. And then we have these laws, which if you look up the fancy term for what all that is, it's a semi-ring. And there you go look up what a semi-ring is. But it's basically all the laws that we talked about that we're used to in sort of high school algebra. Multiplication, addition, There's a 0 for the for addition, and there's a 1 for the multiplication. Okay, now's the fun part. We know what an algebra is. It's this thing that has symbols and operations and laws. Let's do something with them. So I'm going to give you some examples of some tricks that people have figured out, and show you how they're motivated. You can motivate them algebraic. So here's our parts. We're going to talk about laws mostly. The laws are where you can exploit things. So in the laws, so let's say we had the like A plus B equals B plus A. That was a commutative law. So when we say that we're going to exploit that law, it means if we have an expression in one form, we can always turn it into the expression of the other form. So for example, for the commutative one, it doesn't matter what order you do the operations in, but in some circumstances, it may be more efficient to do one operation first versus the other, et cetera, et cetera. So we can sort of pick which side we want to do and transform our expressions one way or the other. So here's some math stuff, and we're going to talk about what this means. So we're going to have a table, and we're going to talk about, and we're going to fill it in with different expressions. So there's going to be, well, maybe I should just start going through it. So here we have in the first column. So in the header there in the blue, there's going to be some type that's called, we're going to call M, and there's another type called N. And this type is going to have some binary operator. So it's some function that takes two arguments and produces another argument. It produces one value. And it's going to have a special value that we're going to call 0 that is of type M. And then there's going to be some other things that we're going to do with M. So in the first example here, on the black row, there's a B, which is going to be Booleans. So this is the type bool, and I didn't have enough room to write Boolean, so I just used B. That's why mathematicians, paper was expensive or something, so they had to write really small. It's really annoying. And so in both, I'm going to have two cases. So M and N, the types M and M and N, which are hard to differentiate verbally, they're both going to be bool. And the binary operator that we're going to talk about is going to be and, which is the hat, and or, which is the more V-shaped operator. And there's going to be special values for these situations, true and false, that we'll see. So one thing that's interesting about Booleans and ands and ors and these special values is that you can convert one into the other. They share a common link between each other that we learned long ago that really bugs us all the time. I can't do Boolean expressions in my head. I always have to write them out, even though I'm old. They're related by another function that we're going to call h in all these circumstances, and that's the not function, the negation function. And they're related by these laws on the right-hand side. So if we just sort of mechanically look, we're saying so on the blue row on the right-hand side, we're saying if you apply h to the 0 of M, you should get the 0 of N. So if we do that for our example in the black row, and h is the not function, so if we say not true is false, okay, that checks out. And then the second equation in the blue row on the right-hand side says, if you apply h to a plus b, then that has to be equal to h of a times h of b, where plus and times are the different operators for M and N. All right, I'm getting into math here, but I'm feeling the audience and everyone's following. So if not, I'm happy to just wanted to pause because I get confused all the time. So if we plug in not as our h there and our and our or operators into plus and times, then we get not A and B is equal to not A or not B, which is the De Morgan law. that we all learned either in math or in programming. And so we can use these facts all the time. We can make our ugly if conditions or else if conditions less ugly by doing these transformations. We can make them clearer. And the meaning, the important part is that through these laws, the De Morgan law, interpreted, at least interpreted this way, we can replace one version with the other. So this is one that we do once in a while. Hopefully you don't have to do it a lot. But you might see it in a code review. Oh, just, you're implicitly using De Morgan's law, and that would make your code so much cleaner because the way you wrote it is ugly. And actually, it works if we reverse them. So they're actually duals of each other. If you switch m and n the opposite way, the laws also hold. So we can get the not of the or is the same as the and of the nots, and vice versa. So that's one example. But other things follow this same pattern. So another example here, instead of Booleans, we're going to talk about numbers, like real numbers. That's what that R is. And we're going to talk about the operations of addition and multiplication. And the special values in addition is going to be 0, which is kind of a normal thing. Like when you add 0, nothing happens. And when you multiply by 1, sort of nothing happens. That's sort of the idea here. So can we relate these two kind of different worlds? Can we relate the world of addition and 0 with the world of multiplication and 1? And one way we can do it, I'm pretty sure there's multiple ways to do it. If we can relate them by an exponential function. Okay, I didn't know this. I just pulled this out of a blog post. It was very exciting. So if we fill in this table, so if this h function is an exponential, then we get some things that we're very familiar with. So e to the x, so e to the 0 of m, so e to the 0 is equal to the 0 of n, which is 1. So that's true. That works out. And then e to the a plus b is the same as the multiplication of e to the a and e to the b. So we get the normal exponent laws here. So these laws are actually really connected to, I hadn't seen them in this form. I always kind of wondered where it came from. Like they were just kind of given, like, because Euler said so or whatever, right? But they're actually, one way to view them is they're coming out of the structure that relates the addition world with the multiplication world. And this is what you get sort of, this is just what happens. So why would I care about that? Well, because of that law, because of this exponential law, I can get this interesting form of it, a specialization of it. So e to the 2a, if I just plug it away, that is, e to the a times e to the a. Now, if we think about programming, if I have some answer that is the result of a calculation times the result of the same calculation, I don't actually have to perform the calculation once. I could compute e to the a once. And I can automatically know the answer is going to be of the form e to the 2a. So I can get I can do less work. So that's sort of like one sort of, if you could formulate somehow the work that you're doing into this, you could say, aha, I only have to do the work once. And I memorize it and I'm done. Here's one that's a little bit more complicated. And I think I have an error in my slides. But that won't stop us. So if we have a type that is, so on the left-hand side in the black, the top one is the type of comparators. So I want to, we're going to use this for sorting. So to do sorting, you need, oh, right. So instead of a function from A to Boolean, it should be a function from two Booleans, a pair of Booleans to a pair of A's to Boolean. You say, is the first one bigger than the second one? And then you say yes or no. And if you can compare two elements, then we can write a sorting algorithm that can compare anything, right? You say, is this value of your type bigger than this other one? And then it puts them all in the right order. So there's my error in my slide, which I probably have known about, but we can fix it. So we have the type of comparators. Then we have the operator that we're going to deal with is the composition of comparators. We can talk about what that means. And then there's going to be a comparator that always says, yes, the first one is always bigger than the other ones. And then we can have, as our M type, are going to be the type of functions. And we're going to have normal function composition, and the zero of function composition is the identity function. So we don't have to really know too much about these, but they're related to each other through this other function h, that is the sort using a particular comparator. So this is how our libraries do sorting. You say, how do you compare things? And then it says, this is, I can sort things for you. So if I sort something with a function that says, I don't care, or I'll always pick the first one, then I'll get no sorting. It's equivalent to only applying the identity function. So you give me a list, and you say, whichever's bigger is the one that is first, then I'll get the same list out, sort of the sort that doesn't do anything. And then we can say that the sort of the composition of comparators is equivalent to sorting by one comparator and then sorting by the other comparator after that sort happened. So you could imagine I have a list of entities. I sort by let's see, what's a good example? A name, okay? So I could, if my name is made up of a first name and a last name, I could sort by the first name and get a list sorted by first names, and then I could sort by last names, and you could get that sorting. Or you could compose the comparators that says you compare the first names, and if those are the same, then you compare the last names, and then you can just do the sort once. So it's a lot of words. The math is much smaller. But basically, you can sort twice using two comparators, or you can compose the comparators and only sort once. And algebra lets you do that. And we do this all the time. Like you want to sort by, when you want to sort by multiple fields, you're sort of implicitly doing this. You're composing the comparators and doing one sort rather than sorting by each comparator repeatedly. Ooh, that was a mouthful. There's one more that's kind of cool. So again, we're going to relate these things via a sort function, but we're going to be dealing with, and the first instance is going to be regular lists with concatenation, and nil is the empty list. And we're going to relate it to lists that are always sorted. So imagine you had a data structure, the sorted list. Whatever's in there is always sorted for you implicitly. And then there's this operator that we're going to call merge, that merges sorted lists. So if we relate these two worlds of lists and sorted lists along with these operators, so obviously sorting the empty list gives you the empty lists. That's cool, because otherwise it would be really weird. Then we can say, by plugging in with these same formulas, the sort of the concatenation of lists is equivalent to sorting each list individually and then merging them. So we can choose which one we want, and we probably want to do the expensive one less. So we would we could say, well, and this is the definition of merge sort if you squint your eyes. So if I can break apart a list into two parts, x's and y's there, if you can partition your list, then I can merge the individual sorts of x and y's using merge, and they should be equivalent. So this is what is the basis of merge sort. And in this case, it's cheaper to break it apart because you can do those parts in parallel and all sorts of other reasons. Merging is fast. Okay, enough of that. Let's get back to Scala. So how do we do this in Scala? So here's something that's kind of fancy looking. It's got this F. It's got this fancy word functor. You may have used a method called map, and lots of things have a map you can call map on, and sort of this trait is talking about the idea of things that have a map method. So any F that takes a type parameter. So F could be list, list takes a type parameter. F could be future, F could be option. So I can have a list of A's, and then if you give me a function from A to B's, I'll give you a list of B's. There's many things that have this map method. We call these things functors. These things called functors have laws just the same as other algebraic things. So if we had a functor F, how would we encode these laws? Because now we're getting to the point, okay, well, we need to write code. We can talk about these equations and these cool identities between the left side and the right side. We got to encode them down. So how do we write them so we can check that our code matches the laws that we want to work out? Well, this is one way we can do it. So we can write out the laws really just as simple functions. So for some types A, B, and C, the composition law for functors says that if you have an F with A's in it, and you have you have a function from A to B, and then B to C, it says that you can map FA with F, and then map the result of that with G, or you can just map FA with the composition F and then G. So this is very much like the other examples where you can compose the maps, or you can do one map with the composition of the functions. And this is one of the functor laws. So if you said, I had a list of strings, and you did map, and you did map, and you did map, and you did map, you could automatically rewrite that, or you could do it manually, to be just one map, where the function you give it is the composition of the functions you gave in the individual section. And this is what happens in frameworks like Spark, and lots of other things, in databases. So all these database optimizations and query rewriting and query optimization, they're all taking advantage of these laws like that. So it's much more efficient to compose the functions and run the map once, because the map, is basically like a table scan, right? So you only want to do a table scan once, and so you compose the functions that you're going to apply to each element, rather than table scanning n times through. So that's sort of a more I don't know if concrete is the right word, but a more day-to-day example. So here's the RDD in Spark, which is the Resilient Distributed Data Set. They have some, underneath there's some iterator over a bunch of values, and so if you were going to map it, you would want to rewrite it. So in this example, I have this. I'm writing my code. I have a representation of it that's an RDD with a bunch of data in it. And so I say blah, 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 dot map, dot map, dot map. But every time we could sort of automatically squish all those functions together with a bit of trickery in the code, so that every time we called map, we didn't actually make a new do another pass on the data. We merely compose our function with the previous function that we got. You can sort of automatically rewrite these things. That's a very crude way of doing it, but you can imagine fancier versions that do some sort of reflection, but this doesn't have any reflection in it. Okay. So there's lots and lots and lots of other things that have sort of this algebraic structure that we try and exploit. So MapReduce is based on this. All the database query kind of stuff. You know, it's better to if you have a filter and a map operation, it's always better to filter first because you get rid of rows that you then don't have to map over. But programmers can write it any way they want, so you want to like rewrite their expressions if they do the filter later. You want to push it early. CRDTs, fold fusion, things to look up later. There's lots of these things that you can say. There's these identities, and you can say which one is better for me to use right now, and transform one expression into the other. Okay, so we have our algebraic structure. We have symbols and operations and laws. The laws are really what's about the exploitation. We're choosing to do one way versus the other way because we know that they are equivalent. We know that they are equal. Yes. Okay. So the last part is trying to say, well, how do we apply this to what we do? You know, like I love math, you love math. We feel lucky when we get to do math. We want to put more math and algebra into our stuff. How do we approach that for our day-to-day job of exciting web services and all that stuff? So domain, what do I mean by a domain? Well, that's really just what we do. So your domain is, I probably shouldn't do Expedia because I'll probably get it wrong, but you know, like I used to work for a cloud storage company. So our domain was, you know, we had users and they had accounts, and the account was under an organization, and the organization had a subscription, and the subscription had certain tiers of storage and sizes, and they're the nouns of the nouns and verbs of your business, the business logic, the stuff you talk to your product owners about, and then you translate into code. That's kind of one description of what we do. So if we were going to take the things that we do in our domain, maybe it would be useful for us to kind of have this schema of an algebra, and maybe that can help us when we write our code and when we encode our domain. So the symbols are the nouns, they're the entities, you know, in our domain. That one's pretty easy. The operations, well, these are the behaviors. This says that when a file is uploaded, then their total storage will increase by the size of the file, and you cannot add a file if the total storage goes over the quota for the organization or something like that. Well, I don't know. That's not really a behavior. The behavior would be, let me pause. Let me undo. That would be like I upload a file, or I add a user to an organization, or the organization changes plans so that their quotas are increased, something like that. The laws are really about the business rules. That says when you can only upload a file if the added size to the current total is not greater than the quota. That's like your business law. That's the law of, you know, the file upload. You don't want that thing violated, or you know, you work with it, right? So these are all the things that, you know, we try to get precision about when we're talking to our product owners and our customers, and we have to translate these into. We want to translate them into these laws, so maybe we can actually kind of do that somehow. So the example I'm going to use is this GitHub micro API. So there's you can post a commit to some user's repo, and you can get that commit by the SHA identity of the commit, the hash of the commit. You know, just a simple sort of write and read operation. So okay, we have this sort of these URLs, these routes or something. What are the entities? Well, here we go. Here's our entities. We have a owner entity and a repo entity, and there's commit and a SHA is kind of a thing. These are all the we're gonna make types for these. The behaviors, well, I can post a commit and I can get a commit. And those are kind of the two operations that I have in this little world. Business, like, what are the rules? What should we say? Like, can you just do this do them in any order with any kind of arguments? Do they interact at all? Well, yeah, there's kind of some meaning there that we want to enforce. So one example would be, well, so how do we encode this? One way we can do it just the simplest possible thing, maybe, is just traits with abstract types. And we have all of our entities as abstract types. I don't even know what the representation of these things are. I just know that there's types for owners and repos and commits and hashes. And so then I can define my operations just as functions in this world. So in my GitHub API, I can get, so if you pass me a value that's an owner and a repo and a SHA, then I'll give you a commit. And post says, well, if you give me an owner, a repo, and a commit, I'll then give you the SHA of the commit that you gave me, and you can use that to look it up. So we can have just types for our entities, for our symbols, and we have functions, which are very normal, nothing fancy there. Functions for our operations. And so maybe it's a little bit, it's not quite as simple as this. So like, what if you ask for a commit that doesn't exist? The owner doesn't exist, the repo doesn't exist, the SHA, a commit with that SHA doesn't exist. You shouldn't get a commit. So that one's a little over constrained, or under constrained, I should say. So we can say, well, for the get method, you give me an owner and a repo and a SHA, and I'll give you a commit, and maybe it won't exist because I couldn't find it. And then for creating, I'm going to give you give me all the inputs, and I'm going to give you this response, and the response is going to be, well, it might have failed, like maybe there's something bad about the input, or I don't know what. So it's either, so if we have this little type alias that says a response is an either, and it's either a failure or a value of type A, and so we're going to create one failure condition. We're going to model like, oh, that commit already exists. So if you try and write the same commit twice, it'll say, sorry, I already have it. Don't, go away. It's fine. I already got that commit. So this might be a little slightly more realistic pair of functions. Like you look up something that might not be there, and when you write it, it'll say, if you already wrote it, it'll say, go away. You don't have to do it anymore. But now that we have these two functions in our domain where we have these types, with a little bit of decoration of these types, we can say how they relate. We can start building up some laws. So we don't have to have these curried views. We can have a more traditional Scala view where we have functions and they have multiple arguments and they have result types. So that didn't change anything. But now we can write some laws. And these laws can also be not really care about the representation at all. For whatever the concrete type is, we can have abstract types for our entities, our owner, repo, commits, and SHAs. And if we have an API, then we can say we can call it like the create law, sort of analogous to like the distributive law or something like that. So if you give me an owner, a repo, and a commit, then it should be true that if I call create, then if it succeeds, which is so create returns an either. The right side of an either is usually the success case, because right is right, the way that I remember it. Left is not right. There you go. So if API create succeeds, then it must be true that the SHA that I received back from the server is the same as the SHA of the commit that I sent it. That should be true. And it should also be true that if I then request that commit by SHA, I should get back an option that has something in it, which is the commit that I sent it. Or if my create is a left, which means it failed, and I got the error value of the commit already exists, then it should be true that for the commit that exists, the owner should be the same, the repository should be the same, and if I get the SHA, it should exist. Like if it says it exists, I should ask, and it should say yes, it does exist. So that it should agree. So we can say all these conditions have to be true about this API, and we don't really have to. We can embellish this with like nicer looking assertion library or a matcher library, but this is basically the logic that we want. Sort of, if I put something in, I should be able to get it back. If I can't put it in, it should already be there. Sort of captures these ideas that we usually write out in sentences and then have to try and figure out how to encode in code. Yeah.
Or like a post.
Laws.
The laws you had earlier.
Yeah.
Like transfer.
Yeah. Yeah.
This is less.
Well, postcondition is really just. Oh, sir. The question is, this looks more like a postcondition than sort of a law that had a sort of a two or more sides that were equivalencies. Well, sort of the left-hand side is the arguments to what I call the law. So for all owner, repo, and commit, the right-hand side, that is equal to the output of the right-hand side. Is it? Well, no, it's really the inputs and the assertion on the output. So it's a transformation of the law into a more sort of predicate form. But that's interesting. I think if we change some of the notation, it's a bit bigger than the law, because if this is how you test, this is the test of the law. The law itself is sort of the Boolean predicates that are in the different branches there. Because say we were going to test a plus 0 equals 0. We would write a function that takes some value of type A, and then we would say, well, A has to equal some function of A that adds 0 to A. And so there's a little bit more structure for the testing. This is the testing of the law with the law inlined inside of it. It's not sort of the law itself. But that's a good question. Okay. So in our domain, we could give it a bit of more structure by talking about our entities as abstract types. And we could have these functions that encode how these entities can be transformed, how they themselves can be transformed, how entities can combine into other entities perhaps. And we have our laws, and they become property-based tests that say these are the conditions that must be true for the entities and the operations that I've defined. And it can be a useful sort of structure to start with when you're working in a domain and trying to figure out how it's supposed to work. And then there's actually an executable that you can get out of it from the functions. Well, you make the types. You have the functions which will be in the code that runs, and you also at the same time get some tests that say these are the conditions that must be true no matter what kind of inputs we have. All right, that was a lot. Appreciate you all listening. So we have this algebraic structure, symbols, operations, and laws, and we can apply it in many, many situations. So it can be, we can be really cool and be in this math stuff, and we can take it all the way to the things that we do in our day-to-day work and apply the structure. And it gives us sort of somewhat of a formalism to apply in many different situations. And what's really nice is the same things keep coming up over and over again. The laws of high school algebra apply to the world of types. They apply to many of the structures. Different laws apply to the structures that we deal with. You take two Legos, you get another Lego. You combine two diffs and you get one big diff. You concatenate two documents, you get one document. A lot of these laws and operations that we deal with in our domains have this mathematical structure, and often we can be lazy if we find it, because then we can use all this machinery that already exists. That's nice. And we can sort of build higher order algebras. So if we have an algebra which describes one thing, we can then use it as sort of, we can compose them together into bigger and bigger ones. Now, it's nice to have that structure. It can be a discipline for how to design what we deal with. But another advantage, or I guess what you get then, is when you have the structure, you can exploit it. So this is sort of picking sides of the identity that make your job easier for a particular task. A lot of examples of this come up in systems like the MapReduce systems or Spark or something like that, where or just databases really, where there's a lot of query rewriting, there's a lot of smarts that take advantage of these laws. You want to get the same answer no matter how you mess with somebody's query. So you need to know what transformations can I do on these expressions that always produce the same answer, but maybe have better runtime characteristics or have better resource usage. They always apply like that. And then we can apply this to our messy world where we're trying to figure out all the business rules. We can use it a bit as a way to structure our thoughts and structure our code to take advantage of perhaps some latent structure that's there. That's all I have, but really thanks for listening. I'm happy to answer any questions either now or just after the fact. Thanks very much.